Dear students, so in previous class we observed that when A and B are bounded, A union B is also bounded. Now, what about the supremum of A union? The result is supremum of A union B is supremum of supremum A and the supremum of supremum A, supremum B. So this is an important result. If A and B are bounded subset of R, then we say that A union B is bounded. Now we have to show that supremum of A union B is supremum of supremum A, supremum B. How to prove this one? So far, clearly A and B are bounded, then their infimum and the supremum are exist. Since A union B is also bounded, then supremum of A union B and infimum of A union B are also exist. So let M1 equals supremum of A, M2 equals supremum of B. Similarly, and N1 equals infimum of A and N2 equals infimum of B. Agree. Now, let M equals supremum of this M1, M2. Choose M in such a way that M is supremum of M1, M2. Okay. Now in previous problem, we saw that if A and B are bounded, A union B is bounded. Since A union B is bounded, supremum of A union B is exist. Supremum A union B exists. Let it be M. Capital M be the supremum of A union B. Okay. Now to show that M equals M, we have to show that M equals M. This is our requirement. How? What is M? It is given M is supremum of A union B. Okay, means A union B is a set. A union B is nothing but a set. Then M is its supremum. Enough? Then what is M? M is supremum of M1 and M2. That means M is an upper bound of M is an upper bound of A union B. Since M is the supremum of A union B and small m is an upper bound of A union B, then clearly we have this M less than or equal small m, mark it as 1. Why? Because M is the least upper bound. M is the least upper bound and M is any upper bound of A union B, surely there is M less than or equals capital M less than or equals small m. Okay. Again, what is M? M is an upper supremum of A union B. Since M is a supremum, moreover, M is an upper bound of A union B. It is a least upper bound. But here we choose this one. M is the supremum of A union B. This M also acts as an upper bound of A union B. Okay. That means, since M is an upper bound, then for all x fallen A union B, clearly by the definition of upper bound, x less than or equals M. Sure? Means x less than or equals M for all x fallen A union B. That means x less than or equals M for all x fallen A and x less than or equals M for all x fallen B. Sure? But what is M1? M1 is supremum of A. Since M1 is supremum of A, means for all x fallen A, this x less than or equals M1. Okay, x less than or equals M1. And what is M2? M2 is supremum of B, so this should implies for all x fallen B, this x less than or equals M2. Combines these results. We have x less than or equals M for all x fallen A and x less than or equals M for all x fallen B. But here x less than or equals M1 for all x fallen A and x less than or equals m2 for all x fallen b. So this should implies this m1 less than or equals m and m2 less than or equals m. Okay. So m1 less than or equals m and m2 less than or equals m means supremum of this m1 and m2 also less than or equals m. What is supremum of m1 m2? We just choose as m. So by the choice m less than or equals m, mark it as 2. Here capital M less than or equals small m and small m less than or equals capital M. So combinedly gives small m equals capital M. That is what we recurse here, or that is our claim. Where capital M be the supremum of A union B and small m be the supremum of A, supremum of A and supremum of B. Okay, so this result that's a well established result. If A and B are bounded, then A union B is also bounded. Moreover, supremum of A union B is supremum of supremum A and supremum B. So, in the same manner, you can show that this infimum of A union B. This result is also important. Infimum of A union B is infimum of infimum A, infimum B. The result is in the same way. You can prove this result in similar manner. So these two results are very important. That is, when A and B are bounded, their union is also bounded. Moreover, supremum of union of any two sets is supremum of the each sets. Supremum of supremum A, supremum B. Similarly, it's infimum. Okay. Now, come to another result. Suppose S is a non-empty subset of 1. Come to a problem. Let S be a non-empty subset of 1. Comma S is bounded above. S is bounded above. Means S is bounded above means its supremum exists. Okay. Let A fall in R. A is any real number. Comma A plus S. S is a non-empty subset of R. A plus S is defined as A plus X, where X fall in S. A is in R and X fall in S. Then prove this. Supremum of A plus S equals A plus supremum S. S is a non-empty subset of. Supremum of A plus S equals A plus supremum S. It's again a very interesting result. S is a non-empty subset of 1 which is bounded above. It is bounded above, hence its supremum exists. Now A, for any real number A, this A plus S is defined as A plus X, set of all A plus X for X fall in S. Then supremum of A plus S equals A plus supremum S. How to prove this one? So listen, its proof is in this way. What is S? S is a non-empty subset of 1. Since S is bounded, its supremum exists. Let U equals supremum of S. Let U equals supremum of S. U equals supremum of S means what is U? U is the least upper bound. Moreover, U is an upper bound. Therefore, for all X fall in S, this X less than or equals U. Okay, X less than or equals U. What is A? Since A is in R, choose A is that A fall in R. It is given A is a real number. Then, since X less than or equals U, surely this A plus X less than or equals A plus U for all X fall in S. A is a real number, X less than or equals U, then surely A plus X less than or equals A plus U. What is this A plus X? A plus X belongs to where? A plus S. Why? A plus S is Nothing but the set of elements a plus x. So a plus x should belongs to this a plus x, since a plus x belongs to a plus s. A plus x less than or equals a plus u implies this a plus u be an upper bound of a plus x. Okay, a plus u be an upper bound of a plus x. Again, let v be an, how many upper bounds are there? We know that there are infinitely many upper bounds. So we choose another upper bound. Let v be an upper bound of a plus s. Let v be an upper bound of a plus s. V be an upper bound of a plus s means, what is the form of element in a plus s? That is a plus x. Therefore, since v be an upper bound, it is a plus x less than or equals v. A plus x less than or equals v means x less than or equals v minus a. X less than or equals v minus a for all x fall in S. Okay. So x less than or equals v minus a for all x fall in S means what is actually v minus a? Again, by the definition of upper bounds, v minus a is an upper bound of S. V minus a is an upper bound of S because x fall in S. Okay. So v minus a is an upper bound of S. V minus a is an upper bound of S. That means, what is u? What is S? U is the supremum of S. Moreover, v minus a is an upper bound of S. Therefore, that means this u less than or equals v minus a. Why? Because u be the supremum of S. U be the least upper bound, and v minus a is another upper bound. So, surely u less than or equals v minus a. Okay, u less than or equals v minus a, that means u plus a less than or equals v. U plus a less than or equals v means least upper bound of, therefore, what is v? V be an upper bound of a plus s, and u plus a less than or equals v, that means this u plus a is least upper bound or supremum of a plus s. Why? Listen, u plus a is less than or equals v. What is actually v? V be an upper bound of a plus s. So there exists another upper bound which is less than or equals v. That means this u plus a is a supremum of a plus s. So a plus u or as u plus a is a supremum of a plus s. Therefore means supremum of a plus s equals u plus or a plus u, that is a plus, what is u? U is supremum of s. So this is our proof, that is supremum of a plus s is a plus supremum of s. Agreed. Similarly, you can show this another result, infimum of a plus s equals a plus infimum of s. This is again by the same arguments. Okay, thank you.